Our solar system is not the orderly neighborhood we once thought it was. Scientists are confronting 25 cosmic anomalies that defy our basic understanding of physics. By the end of this journey, you will know the most baffling puzzles that astronomers are trying to solve right now. We will explore a planet spinning on its side and a moon shooting geysers into the void. What do you believe is the solar system's greatest secret? High above the swirling pastel clouds of Saturn, a geometric giant keeps watch. A perfect hexagon, wider than two Earths side by side, encircles the planet's north pole. This is not a fleeting cloud formation but a permanent fixture, a six-sided jet stream with winds screaming at over 300 kilometers per hour. It was first glimpsed by the Voyager probes decades ago and later marveled at by Cassini, yet its origin remains one of the solar system's most captivating puzzles. How can a perfect geometric shape emerge and hold its form in the chaotic, turbulent atmosphere of a gas giant? Scientists have run complex simulations, suggesting it could be driven by deep atmospheric waves or a unique type of polar vortex. But no model has yet been able to fully replicate the hexagon's startling stability and razor-sharp edges. It stands as a monumental lesson in humility, showing us that the laws of fluid dynamics can create art far beyond our imagination. And just next door, another world presents an atmospheric mystery that is equally bizarre, but for a very different reason. While Saturn's hexagon is a visible marvel, Jupiter conceals a far more powerful and deeply strange secret. This giant's magnetic field is the strongest we know, a colossal, invisible shield stretching millions of miles into space. Yet the Juno spacecraft discovered it is profoundly lopsided, a cosmic imperfection that has left scientists rethinking everything. In the north, the magnetic field is intensely concentrated and powerful, while the southern hemisphere presents a broader, much weaker and more complex structure. This is not how a planetary magnetic field should behave. According to our best models, the dynamo effect, where a planet's rotating, electrically conductive interior generates a magnetic field, should produce something far more symmetrical. Think of it like spinning a perfectly symmetrical ball of fluid. The magnetic field it creates should be roughly even at both poles. Jupiter's field is anything but even. This points to a turbulent and uneven reality deep within the planet's heart, far beneath its striped cloud tops. The core is not a uniform sphere of metallic hydrogen. Instead, scientists now speculate there could be vast, isolated regions of extraordinary conductivity, or chaotic, lopsided flows of liquid metal that act like separate dynamos, all churning against each other. It is a hidden, unbalanced engine of immense power, defying the elegant simplicity of our textbooks. If the solar system's largest planet can have such a fundamentally flawed magnetic heart, what other internal surprises might be waiting on the smaller, seemingly simpler worlds orbiting closer to the Sun? This profound asymmetry in Jupiter's magnetic field pales in comparison to the wholesale reorientation of an entire world. Uranus does not spin like a top, it rolls around the Sun like a ball. Its rotational axis is tilted a staggering 98 degrees, placing its poles where its equator should be. For nearly half of its 84-year orbit, one pole is locked in perpetual sunlight, while the other is plunged into an equally long, frigid night. This bizarre configuration points to a truly violent birth. The prevailing theory is that in the solar system's chaotic youth, a protoplanet at least the size of Earth slammed into the young Uranus, knocking it completely onto its side. But this elegant solution creates a new puzzle of its own. If such a catastrophic impact occurred, Why do the planet's rings and 24 moons all orbit perfectly in line with its tilted equator? A colossal collision violent enough to topple a giant planet should have shattered any early moons and sent debris flying into wildly different orbits. It is as if the entire Uranian system, the planet and all its companions, were tipped over in one single, cohesive piece. This forces astronomers to consider alternative, even stranger histories. Perhaps it was not one single impact, but a series of smaller, grazing collisions that gradually talked the planet over. Or maybe gravitational tugs from a since-ejected giant planet slowly pulled Uranus into its sideways roll. The mystery only deepens when we feel for its warmth. Unlike its similar-sized sibling Neptune, which radiates intense internal heat, Uranus is curiously cold, emitting barely more energy than it receives from the distant Sun. Did the same impact that tilted it over also scramble its core, somehow locking away its primordial heat? Or does its unique orientation cause its atmosphere to somehow trap energy more efficiently? The sideways world remains a frozen enigma, a testament to a formative era of planetary violence whose story we are still struggling to read. Even the fractured history of Uranus pales next to the shattered face of its own moon, Miranda. This is a world that defies all logic, a cosmic jigsaw puzzle assembled by a seemingly careless hand. Its surface is a chaotic patchwork of ancient, cratered terrain abruptly meeting vast, young plains scarred by canyons so deep they could swallow Mount Everest whole. But the most bizarre features are its coronae, three vast trapezoid-shaped regions of parallel ridges and grooves that look like giant racetracks etched into the ice. These are not subtle markings, they are colossal geological structures, some with cliffs towering 20 kilometers into the black sky. How does a moon barely 500 kilometers across, a tiny frozen world, muster the energy for such extreme geology? The leading theory is one of cosmic destruction and rebirth. Imagine Miranda being struck so hard by an ancient impactor that it was blown completely apart. Then, over eons, its own gravity painstakingly pulled the fragments back together, a haphazard reassembly that left its deepest, warmest interior material exposed in those strange, grooved coronae. Yet this violent story is hotly debated, for no other moon we have ever seen displays such a fragmented and varied landscape. If it was not a shattering impact, then what other force could have twisted this small moon so brutally? Perhaps tidal forces from Uranus's immense gravity stretched and kneaded its interior, generating enough heat to drive unimaginable tectonic upheavals. But the energy required seems too great for such a distant, frozen orbit. Miranda remains a stark reminder that even the smallest worlds can hold the most violent secrets, frozen in time for us to decipher. And if a small, icy moon can harbor such geological ferocity, what strange energies might be at work on another, even more distant icy body, one that actively spews its own inner ocean into the void of space? While Miranda is a frozen relic of ancient chaos, the tiny moon Enceladus is a world defiantly alive. From the brilliant, cracked ice of its south pole, enormous geysers blast water vapor and ice crystals hundreds of miles into the blackness of space. The Cassini spacecraft did not just see these plumes, it flew right through them, tasting their contents in a breathtaking maneuver. The analysis was stunning. These are not simple jets of water, but a complex soup containing salty ice, silica nanoparticles, and a rich assortment of organic molecules like methane, propane, and acetylene. The source is a vast, global ocean of liquid water, trapped between the moon's rocky core and its icy shell. For a world so small and so far from the sun, this revelation was extraordinary. How can this tiny moon, a mere 500 kilometers across, sustain a liquid ocean and such explosive activity? The engine is believed to be the immense gravity of its parent planet, Saturn. As Enceladus travels along its slightly elliptical orbit, Saturn's gravitational pull relentlessly squeezes and flexes the moon's interior. This tidal friction generates immense heat, enough to keep the subsurface ocean from freezing and to power the spectacular cryovolcanism. Yet the sheer vigor of these eruptions, continuously replenishing the ocean and blasting material into space, pushes our understanding of tidal heating to its limits. The process is so effective that the geysers themselves have become part of Saturn's architecture. The ice particles they eject form a faint, diffuse ring around the planet, known as the E-ring. This creates a profound cosmic connection, where the internal dynamics of a tiny moon directly shape the environment of a gas giant. The discovery of a warm, salty, and chemically rich ocean on Enceladus instantly transformed it into one of the most promising places to search for life beyond Earth. It possesses all the key ingredients: water, energy, and the building blocks of chemistry. This forces a fundamental question. If a small, icy moon can harbor such a habitable environment, what other hidden oceans might be lurking in the darkness, perhaps on a world even more massive and mysterious than Enceladus? The promise of a hidden ocean on Enceladus finds a grander, more complex echo around Jupiter. Europa's surface is a cracked and frozen canvas, a global ice shell covering a saltwater ocean deeper than any on Earth. But this shell is not a placid, solid lid. Vast stretches of its surface are shattered into what scientists call chaos terrain. These are not simple cracks, but sprawling regions where giant blocks of ice, some the size of cities, have been broken apart, tilted, and refrozen into a new, bewildering mosaic. It looks as if a colossal hammer struck the world's frozen crust, and the pieces haphazardly settled back into place. This widespread chaos is a direct signal that Europa's icy shell is geologically alive. The leading idea is that warmth from the ocean below rises, partially melting the base of the ice. This creates buoyant plumes of warmer, softer ice that slowly push upward, a process known as diapirism. These rising blobs of ice might warp and fracture the brittle surface from below, causing it to collapse and rearrange into those chaotic blocks. In some models, the ocean might even make direct contact with the surface through these fractures, briefly exposing the deep water to the vacuum of space before it refreezes. This constant churning is a potential gateway, a way for chemicals and energy to move between the surface and the ocean. If the ocean holds the ingredients for life, these chaotic terrains could be the very spots where surface minerals, altered by Jupiter's intense radiation, are carried down to nourish whatever might dwell in the dark. Yet, for all its explanatory power, this model struggles to account for the sheer scale and intricate jigsaw puzzle appearance of the chaos. Computer simulations have a difficult time recreating the specific, widespread patterns we see. This suggests our understanding of ice physics on a planetary scale is still incomplete. What forces exactly can torque and rotate such massive ice flows with such apparent randomness? The answer may lie in a combination of processes, from the slow convection of the ice shell itself to the immense tidal stresses exerted by Jupiter's gravity. This dynamic ice world presents a stark contrast to another Jovian moon, one where the internal heat escapes not through fractured ice, but through the most violent volcanoes in the solar system. The churning ice of Europa stands in stark contrast to the fire of its neighbor, Io. This is a world painted in the violent hues of sulfur and silicate rock, a moon so relentlessly volcanic that its entire surface is remade before our very eyes. Jupiter's fierce gravity does not gently squeeze this world as it does Europa. It violently needs it. The immense gravitational pull from Jupiter, combined with precise tugs from the sister moons Europa and Ganymede, stretches and compresses Io's interior with such force that its very rock melts. This creates a global ocean of magma, or at least vast churning layers of molten rock just beneath the crust. The result is a landscape of fire. Hundreds of active volcanoes continuously erupt, spewing fountains of lava dozens of miles high and painting the surface in broad, fresh strokes of yellow, red, and black. Plumes of gas and dust soar so high they are visible from telescopes on Earth. The sheer power being released within this moon is staggering, orders of magnitude greater than all the volcanic and geothermal energy of our entire planet combined. This extreme output challenges the very limits of our physics, forcing scientists to ask how tidal heating can be so devastatingly efficient. The mystery deepens when you look at a map of Io's volcanoes. They do not appear where our best models predict the tidal stress should be greatest. Some regions are bizarrely quiet, while others erupt with unexpected fury. This suggests that Io's internal structure is far from uniform. There could be vast, asymmetric pockets of molten rock, or a core that is oddly shaped, focusing this incredible heat in unpredictable ways. Io is a testament to the raw, untamed power of gravity, a world being torn apart from the inside out even as we watch. This display of immense orbital forces shaping a small world makes us look at another system defined by gravity, the intricate and perplexing rings of Saturn. The raw, untamed volcanism of Io is a spectacle of pure force, yet around Saturn, gravity performs a far more delicate and intricate dance. Here, two tiny moons engage in a perpetual tug of war over a slender ribbon of ice. This is the F-ring, a structure so narrow and sharp it seems drawn with a cosmic ruler, and its stability is an illusion. The moons Prometheus and Pandora are its shepherds, orbiting just inside and outside the ring's path. Their gravity gently herds the countless ice particles, preventing the ring from spreading out and fading into nothingness. But Prometheus is a chaotic shepherd. On its slightly elongated orbit, it swoops in close to the ring's inner edge every few years. As it approaches, its gravity does not just nudge the particles, it violently stirs them. It drags out long, dark channels and brilliant, transient streamers of ice that can stretch hundreds of kilometers across the void. These are not permanent features but fleeting scars, beautiful evidence of a system in constant, unpredictable flux. The standard equations of orbital mechanics struggle to forecast the precise patterns Prometheus will carve on its next pass. This suggests that other, unseen forces are at play. Perhaps unseen moonlets, no larger than a kilometer across, are hidden within the ring itself, their tiny gravitational nudges adding to the turbulence. The very existence of this delicate system is a puzzle in itself. How do these small moons perform their gravitational ballet for eons without being shattered by impacts or dragged into the ring they are trying to control? Their orbits hold clues, showing subtle resonances and deviations from perfect Keplerian paths that hint at a long and complex history of migration. They may not have formed where they are today, but were instead pushed and pulled into their current positions by interactions with other moons or with the ring material itself. This fragile, dynamic arrangement around a gas giant forces us to look at the faint, dark rings of the ice giants and wonder. Could similar, unseen shepherds be at work there, maintaining rings in the profound darkness of the outer solar system? And if such delicate gravitational balances can exist, what other, far stranger orbital partnerships might be hiding in the vast expanse between the planets, in a region ruled not by a giant world, but by the sun itself? Neptune's deep blue visage, once adorned with brilliant white cloud bands and churning dark storms, is fading before our eyes. Decades of monitoring show its most prominent features can vanish in just a few years, a stark contrast to the enduring fury of Jupiter's Great Red Spot. The Great Dark Spot witnessed by Voyager 2 was a storm the size of Earth itself, yet by the time the Hubble Space Telescope looked again, it was gone without a trace. This is not a placid, frozen world but a cauldron of meteorological chaos. The driving force behind this violent weather presents a fundamental puzzle. At Neptune's vast distance, the Sun is little more than a bright star, providing only a faint whisper of energy. The engine for this turbulence must come from within, from the immense internal heat left over from the planet's violent formation billions of years ago. This heat rises through the planet's deep atmosphere, churning its mix of hydrogen, helium, and methane into colossal storms and complex cloud systems. Yet our models cannot fully explain the speed and scale of these changes. How can a storm larger than our entire planet form, rage, and then simply dissipate into calm blue haze in such a short cosmic timespan? The answer may lie in the delicate balance between this outpouring of internal heat and the upper atmosphere's response. Unlike Jupiter or Saturn, Neptune's weather may operate on a knife's edge, where slight shifts in heat flow or atmospheric chemistry can trigger a planet-wide metamorphosis. This volatility on a distant ice giant makes us wonder what other fragile systems might be on the verge of change. Could a world not just change its appearance, but actually be coming apart at the seams? Even the fleeting storms of Neptune are outshone by the ongoing spectacle of its largest moon. Triton is a world of profound contradictions, a captured wanderer from the distant Kuiper belt, now forced into an unnatural orbit. It circles Neptune backwards, moving in the opposite direction of the planet's own spin. This retrograde path is the definitive clue that Triton is not a native of this system, but an immigrant snatched by Neptune's gravity from the frigid depths billions of years ago. Its surface is not the ancient, cratered landscape you would expect from such an old, cold body. Instead, it is bizarrely young, smooth, and astoundingly active. Voyager 2 spotted dark plumes rising several kilometers into its thin atmosphere, geysers of nitrogen gas and dark dust erupting from beneath an icy crust. These are not volcanoes of fire, but of ice, powered by an internal warmth that defies all logic. The entire surface is a dynamic canvas, resurfaced by a wandering layer of nitrogen frost that shifts with Triton's long, slow seasons. How can this small, captured world remain so geologically vibrant? The primary suspect is tidal heating. When Triton was first captured, its orbit would have been wildly elliptical. The relentless, changing pull of Neptune's gravity would have stretched and squeezed the moon's interior, generating immense frictional heat. This process should have subsided as Triton's orbit gradually circularized over the eons. Yet here we are, billions of years later, and the moon is still erupting. This is the core of the mystery. Where is the heat coming from now? The tidal forces on its current, nearly circular orbit are far too weak to power such activity. The answer must be locked inside its hidden structure. Perhaps Triton possesses a deep, insulating layer of frozen nitrogen that acts like a blanket, trapping the primordial heat from its violent capture for billions of years. Or maybe its rocky core is laced with radioactive elements that provide a slow, steady trickle of warmth, enough to keep its subsurface ocean of ammonia and water from freezing solid. The presence of such an ocean would explain the ease with which material reaches the surface, but it raises even more questions about the moon's internal chemistry and resilience. Triton forces us to reconsider the very definition of a dead world, and to look at every captured, irregular moon in our solar system with new, questioning eyes. If a lone wanderer like Triton can hold onto such vibrant energy for so long, what other dormant giants might be hiding in the dark, their internal fires merely sleeping? The wild, looping path of Neptune's moon Nereid is a cosmic roller coaster unlike any other. Its orbit is not a neat, circular path but a lopsided ellipse of breathtaking extremes. On its closest approach, Nereid swoops to within 840,000 miles of Neptune, only to swing out to an astonishing 6 million miles away at its farthest point. This is not a native moon born from the planet's accretion disk, but a captured wanderer, a relic from the solar system's earliest days. Nereid is part of a much larger family known as irregular moons. These are the strays of the planetary system, small, often misshapen objects orbiting the giant planets at vast distances, on paths that are wildly eccentric, highly tilted, or even backwards. Their very existence tells a story of a violent, chaotic young solar system, but the precise chapter of their capture remains a frustrating blank. How does a free-flying object from the Kuiper belt get snared by a planet's gravity without either crashing into it or simply flying past? One theory involves a complex gravitational dance, where a passing object interacts with both the planet and another large moon, losing just enough energy to be captured. Another idea suggests that in the solar system's infancy, the planets were still surrounded by extended disks of gas, and the drag from plowing through this material could have slowed a transient object into a bound orbit. A third, elegant proposal is that many of these objects were not alone but were part of binary pairs. As this pair swung close to a giant planet, the planet's gravity could have torn the duo apart, capturing one member and flinging the other away into interstellar space. Yet each of these scenarios has its flaws. The gas drag model struggles to explain the capture of the most distant irregular moons, while the binary dissociation theory has a hard time accounting for the sheer number and variety of orbits we observe. These captured moons are frozen time capsules holding pristine material from the era of planet formation, but their chaotic, tangled orbits are like a scrambled index, making it incredibly difficult to piece together their true origins and, by extension, the precise conditions of that ancient time. If the histories of these small, captured moons are so difficult to read, what does that say about our ability to classify the countless smaller, fainter objects drifting in the vast spaces between the planets? Far out in the solar system's deep freeze, a world is spinning itself into a new shape. The dwarf planet Haumea, a resident of the distant Kuiper belt, whirls with such ferocious speed that it can no longer hold a sphere. It completes a full rotation in less than 4 hours, a blur of motion that has stretched its form into something resembling a flattened football or a cosmic river stone. This is not a gentle wobble but a violent, centrifugal force overpowering gravity itself, creating one of the most distorted large objects we know. The leading theory points to a catastrophic origin, a colossal impact billions of years ago that sent the young world into a dizzying spin. This ancient collision is believed to have done more than just set it whirling. It also blasted material into space that coalesced into Haumea's 2 small moons, Hioka and Namoka, and even created an entire family of smaller, icy fragments that now share its orbit around the Sun. Yet, recreating this precise cosmic strike in computer simulations has proven incredibly difficult. The exact angle, speed, and size of the impactor needed to impart such a rapid rotation without utterly shattering the planet remain elusive. To further complicate the mystery, Haumea's surface is coated in an unusually bright and crystalline form of water ice. This is strange because radiation in space should, over eons, break down the orderly crystal structure and darken the ice into an amorphous state. Its pristine, shiny surface suggests recent geological activity or a process that somehow refreshes the ice. But how does a seemingly inert, rapidly spinning rock manage such a feat? Could the immense forces from its spin generate enough internal heat to cause resurfacing? Or are we misunderstanding the chemistry of these distant objects entirely? Haumea stands as a stark challenge to our models of cosmic collisions and planetary stability, a world whose very form defies expectation. If a violent impact can sculpt a world into such a bizarre shape, what other cosmic accidents might have created objects that are not just misshapen, but actively falling apart? The bizarre, spinning shape of Haumea seems almost simple compared to the object the Rosetta spacecraft chased across the solar system. Comet 67P, or Churyumov-Gerasimenko, is not a single, round world. It is a cosmic rubber duck, a 4-kilometer-wide body composed of two distinct lobes connected by a fragile, narrow neck. This is not a fragment from a violent break-up, but a structure that appears to have formed from a gentle, almost tender union. The prevailing theory is that in the solar system's earliest days, two separate cometesimals, each a primordial snowball of ice and dust, drifted together at walking speed and stuck, merging into this single, bilobed entity. This gentle accretion process is a window into the most fundamental building blocks of planets, showing how tiny grains could have clumped into ever larger bodies. Yet this peculiar shape is not just a static relic, it actively governs the comet's life. As 67P swings closer to the Sun and heats up, its most dramatic activity erupts not from the large lobes but from that fragile neck. Intense jets of gas and dust blast out from this region, acting like natural thrusters. These eruptions subtly change the comet's rotation and nudge its path through space, meaning its very shape is slowly steering its own destiny. The central debate is whether this form truly came from a gentle merger, or if a single, larger comet was sculpted over eons by uneven sublimation, its middle worn away until only the neck remained. The rubber duck shape is surprisingly common among small asteroids and comets, suggesting this is a fundamental, stable structure. But how can such a tenuous connection, a bridge of loosely packed ice and rock, withstand the forces of its own violent outgassing and the gravitational tugs of planets over billions of years? Its continued existence challenges our understanding of the internal strength of these primordial objects. They are not solid rocks, but fluffy, fragile piles of rubble, yet they possess a cohesive strength that defies their appearance. The story of Comet 67P forces us to reconsider what holds a world together, a question that becomes even more critical when we look at other small bodies that are not just oddly shaped, but actively disintegrating before our eyes. These so-called centaurs are cosmic hybrids, and their behavior is deeply erratic. Orbiting on unstable paths between Jupiter and Neptune, they are minor planets caught in a gravitational crossfire. What makes them truly bizarre is their light. From our vantage point, they can flare into brilliance without warning, their brightness soaring by several magnitudes in a matter of hours. This is not the gentle, rhythmic pulse of a spinning, irregularly shaped rock. This is a sudden, violent eruption of light. The most plausible explanation is that they are outgassing, much like a comet. Vast plumes of volatile gases, perhaps carbon monoxide or ammonia, burst from beneath their surfaces, launching reflective dust into the void around them. This creates a temporary, brilliant atmosphere that dramatically amplifies their glow, but the triggers for these outbursts remain utterly mysterious. One possibility is internal heat from the slow decay of radioactive elements in their rocky cores, building pressure until the surface cracks open. Another is a constant, silent rain of micro-impacts, tiny pebbles striking their surface with enough force to punch through a crust and release trapped gases below. A more cyclical theory involves their wildly changing orbits. As a centaur slowly drifts closer to the Sun on its long journey, ices on or just below its surface might warm enough to transform directly from solid to gas, a process called sublimation, causing a seasonal eruption. Yet no single theory fits every event. Some outbursts are too violent, too sudden, to be explained by gradual solar heating. The existence of these active centaurs shatters our traditional categories. We once neatly divided the solar system into rocky asteroids and icy comets. But these objects are a chaotic blend of both, large enough to be considered asteroids yet behaving with the volatile temperament of comets. They force us to admit that activity is not confined to the solar system's frozen outskirts. It can ignite unpredictably, even in the population of ancient rocks much closer to home, within the main asteroid belt itself. Our own moon, that familiar companion in the night sky, holds a profound secret in its path. It does not circle Earth along our equator's line, but follows a path tilted by 5 degrees. This subtle slant is a major problem for the most accepted story of its birth. That story tells of a cataclysm when a Mars-sized world named Theia smashed into the young Earth. The debris from this colossal impact should have coalesced into a moon orbiting neatly in the plane of Earth's equator, much like the rings of Saturn circle that planet. Yet our moon clearly does not, so what gave it that 5-degree kick? To explain this, astronomers have had to introduce more chaos into an already violent tale. Perhaps in the frenzied early solar system, the newly formed moon was gravitationally jostled by close encounters with other leftover planetary embryos. Or maybe the entire Earth-Moon system went through a phase of extreme gravitational interplay, a dynamic instability that pushed the moon into its slanted path before things settled down. These solutions work in theory, but they feel like adding epicycles to a flawed model. The mystery deepens when we examine the moon's very substance. Its composition is strikingly similar to Earth's own mantle, which strongly supports the giant impact idea. But subtle differences in the chemistry of certain elements, like tungsten and potassium, are hard to reconcile with a straightforward collision. It is as if the moon is almost a perfect copy of Earth, but not quite. This forces us to consider even more complex and energetic impact scenarios, perhaps involving a faster spinning early Earth or a glancing blow from a larger impactor. The quiet, steady presence of our moon belies a genuinely violent and still poorly understood origin. This fundamental uncertainty about our closest neighbor makes us look at the countless other moons orbiting distant planets and wonder, how many of them also hold orbital secrets that defy their own creation stories? And what does that say about the true nature of planetary formation across the cosmos? The mystery of our moon's violent birth finds a parallel in the enigma of another world's lost youth. Mars today is a frozen, rust-colored desert, but its ancient surface is carved with the unmistakable scars of rivers and lakebeds. This presents a profound contradiction known as the faint young sun paradox. Climate models tell us that in those early days, our sun was 30% dimmer than it is now. Under that faint young star, Mars should have been a global ice ball locked in a deep and permanent freeze. Yet the geological record screams otherwise, showing clear evidence that liquid water once flowed freely there. So how was this possible? How could a world so far from a faint sun maintain a climate warm enough for rivers to run? The leading suspect is a much thicker atmosphere, a dense blanket of carbon dioxide that created a powerful greenhouse effect, trapping what little solar heat arrived. But there is a problem. the amount of carbon dioxide needed to warm the planet that much would have left behind specific carbonate rock formations, and our rovers have not found nearly enough of them. This forces scientists to consider other, more potent greenhouse gases like methane, which could have provided a temporary super-warming punch. Or perhaps Mars's early warmth was not constant, but came in brief, intense bursts driven by dramatic shifts in its orbit and tilt, periods where the polar ice caps melted and sent torrents of water across the landscape. Even these clever solutions, however, struggle to explain the sustained, stable periods of water flow that the geology implies. The paradox does not just ask how Mars was warm, but how it stayed warm for long enough to carve its intricate valleys. And this leads to an even deeper puzzle. Where did that life-giving atmosphere go? The prevailing theory is that as the planet's molten core cooled, its global magnetic field shut down. Without this protective magnetic shield, the solar wind, a relentless stream of charged particles from the sun, began to systematically strip the atmosphere away, molecule by molecule, over hundreds of millions of years. This slowly bled the planet of its insulating blanket, turning a potentially habitable world into the freeze-dried desert we see today. Yet the precise sequence of this great dying, the exact interplay between atmospheric loss and climate collapse, remains one of the greatest unresolved stories in our solar system. If a world like Mars could lose its habitability so completely, it forces us to ask what delicate balances maintain a stable climate on any planet, including our own. This question of a lost atmosphere brings us to a modern Martian mystery, one that puffs gas into the thin, cold air of the present day. The thin, cold air of Mars holds a ghost, a chemical specter that appears and vanishes without warning. This is the mystery of Martian methane, a gas that should not be there. Rovers like Curiosity have repeatedly sniffed out tiny, transient plumes of this gas in the crater where it roams. From above, orbiting spacecraft have sometimes confirmed these fleeting pockets, mapping them to specific regions. The puzzle is not just its presence, but its behavior. Methane is a fragile molecule in the Martian atmosphere, quickly broken apart by the sun's harsh ultraviolet light and chemical reactions with other compounds. It should last for centuries, yet on Mars it seems to vanish in a matter of weeks. What process can create it so quickly and then destroy it even faster? On our own planet, methane is a powerful signature. Vast quantities are belched out by living organisms, from microbes to livestock, but it also seeps from non-living sources through a geological process called serpentinization, where water interacts with specific minerals like olivine deep underground, releasing the gas as a byproduct. So the great question hanging over the red planet is this: are we seeing the faint, lingering breath of subsurface Martian microbes, or simply the slow, geological digestion of rocks? The evidence frustratingly points in both directions. The gas appears sporadically and locally, not in a steady, planet-wide haze, suggesting small, isolated sources. Yet no known geological process we understand can easily explain the rapid bursts and the even more rapid disappearance. Could there be an unknown catalyst in the Martian soil, a mineral that accelerates the destruction of methane, scrubbing it from the air almost as soon as it appears? Or perhaps the source is not production at all, but the sudden, timed release from ancient underground reservoirs where the gas has been trapped for eons in ice-like structures called clathrates. Each time a pocket ruptures, it vents a brief, telltale plume before sealing itself shut again. This unresolved tug of war between a potential sign of life and a purely abiotic explanation makes the methane one of the most tantalizing and frustrating puzzles in modern planetary science. It forces us to admit that Mars, a world we see as a static desert, might be subtly, mysteriously active right under our robotic noses. And if a world with such a thin atmosphere can host such a complex chemical mystery, what astonishing secrets might be hidden beneath the thick, crushing clouds of our own sister planet, Venus? While Mars teases us with faint whispers of methane, Venus presents an atmospheric drama of operatic scale. Its entire sky is a runaway carousel, spinning at a ferocious speed that defies the planet's own lethargic role. At the blistering cloud tops, hurricane-force winds scream around the globe, completing a full circuit in just 4 Earth days. Yet the scorched rock below takes 243 days to complete a single, agonizingly slow rotation. This is superrotation, a phenomenon where the atmosphere moves 60 times faster than the planet it envelops. What colossal engine could possibly drive and sustain this perpetual planet-wide gale? The leading suspect is thermal tides. On Earth, our tides are governed by the gravitational pull of the Moon, rhythmically swelling the oceans. On Venus, the Sun's intense heat creates a different kind of tide, a massive, daily bulging of the superheated atmosphere itself. This solar-powered push, combined with momentum transported by vast, planetary-scale waves churning within the clouds, may be the hidden force that keeps the atmospheric carousel spinning. But our models struggle to replicate the sheer power and stability of this system, leaving a gap in our understanding of how fluid dynamics operate on a global scale. This runaway atmosphere is tied to an even greater cataclysm. Venus is a desert in the most profound sense, a world stripped bare of water. Measurements of its atmosphere reveal a crucial clue: a dramatically elevated ratio of deuterium, a heavy form of hydrogen, to normal hydrogen. This is the fingerprint of a planetary-scale escape. The leading theory is that Venus once possessed vast oceans, but as the young sun grew brighter, the planet experienced a runaway greenhouse effect. Water vapor, a potent greenhouse gas, flooded the atmosphere, trapping more and more heat in a vicious cycle that eventually boiled the oceans away. High in the atmosphere, ultraviolet light from the sun then broke the water vapor molecules apart in a process called photodissociation. The lightweight normal hydrogen, freed from the heavier oxygen, was then easily swept away into space by the solar wind. The heavier deuterium, however, was more likely to be left behind, creating the enriched ratio we see today. Yet this story of a slow, tragic drying is not fully settled. The sheer efficiency required to remove an ocean's worth of water is staggering, and some scientists wonder if a more catastrophic, rapid loss event occurred. These two great puzzles, the whipping atmosphere and the vanished ocean, are almost certainly intertwined. The same solar energy that drives the superrotation also powered the photodissociation that broke the water apart. The loss of the oceans, in turn, would have fundamentally altered the chemistry and dynamics of the atmosphere, perhaps locking it into its current violent state. Venus stands as a stark monument to climate catastrophe, a world that may have once been a twin to Earth but veered onto a hellish path. Its extreme conditions force us to ask what delicate balance maintains our own planet's hospitable atmosphere, a system that also holds its own profound and unanswered questions. Our own planet is locked in a gravitational embrace with a partner of extraordinary size. The Moon is not a mere satellite. It is a companion world so large that the Earth and Moon are often described as a double-planet system. This is a profound rarity among the rocky worlds. Mars has only tiny, captured asteroids for moons, and Venus and Mercury have none at all. Our situation is special, and this cosmic partnership has shaped the very existence of life. The Moon's immense gravity acts as a steadying hand on the Earth's shoulder, dampening the chaotic wobbles in our planet's axial tilt. Without this lunar anchor, our world would experience wild, unpredictable swings in its orientation to the sun. Poles could migrate toward the equator over millions of years, triggering radical climate shifts that would turn our stable seasons into a global roller coaster of ice and fire. This long-term climate stability provided by the Moon is considered a crucial, hidden ingredient, allowing life the steady environment needed to evolve from single cells into the complex tapestry we see today. Yet this vital relationship is not static. The Moon is slowly drifting away from us, at a rate measured by lasers bouncing off retroreflectors left by Apollo astronauts. While the average rate of recession is known, the data contains small, unexplained jitters, tiny deviations from the predicted path. These minuscule anomalies are whispers from the deep past, hinting that the Earth-Moon system's dance has not always been so smooth. Perhaps gravitational encounters with other large bodies in the early solar system slightly perturbed our orbit, or maybe changes in the shape of Earth's oceans over geologic time altered the tidal forces at play. Beyond stabilizing our climate, the Moon's pull is a constant physical sculptor of our world. It drives the ocean tides that churn nutrients through the seas, and its gentle, relentless tug creates friction within Earth's crust and mantle. This internal tidal heating, though subtle, contributes to the simmering energy of our planet's interior. The Earth-Moon system is thus a unique laboratory, a place where we can study how a massive moon influences a planet's rotation, climate, and even its internal geology. This special bond makes us look differently at the countless binary asteroids and distant Kuiper belt objects that also orbit each other, wondering if any of those distant, frozen pairs might also be nurturing a hidden stability of their own. Deep within the main asteroid belt, two worlds dance in perfect, silent balance. This is the Antiope system, an asteroid that revealed itself to be not one, but two nearly identical bodies, each about 90 kilometers across, eternally circling one another. They are not a primary body with a tiny moon, but a true binary pair, a cosmic couple locked in a 16-hour waltz. A gap of 171 kilometers separates them, a distance they maintain with gravitational precision. How does such a perfectly matched pair come to exist? For asteroids of this size, such an arrangement is incredibly rare. The most intuitive idea, a catastrophic collision, does not fit. A violent, high-speed impact would likely shatter both bodies, creating a chaotic debris field, not a stable, elegant duet. The formation must have been far more gentle, perhaps a slow, grazing encounter where two independent asteroids gently captured each other, losing just enough energy to become bound. Another compelling theory points to spin. A single parent body spun up by the subtle but relentless pressure of sunlight, a phenomenon called the Oort effect, could have eventually fissioned, tearing itself in two. Yet, for this to result in two nearly equal halves that then settle into a stable orbit, instead of just spraying fragments everywhere, requires a precise and unlikely set of conditions. The existence of Antiope forces a rethinking of the main belt's history. It is not just a realm of violent shattering and chaotic impacts, but also a place where delicate gravitational ballast can be arranged and preserved for eons. This perfectly balanced pair of asteroids makes us look closer at the smallest, most fleeting members of the solar system, objects that are not just orbiting, but are actively falling apart. Far beyond the familiar orbits of the planets, in the deep freeze of the outer solar system, a population of icy worlds is behaving as if they are being herded. These are the Trans-Neptunian objects, and their paths are not random. A surprising number of them are clustered together, their elongated orbits pointing in the same general direction and tilted at similarly sharp angles away from the flat plane of the solar system. This is not what we would expect from a quiet, undisturbed region. It is the astronomical equivalent of finding a dozen compass needles all stubbornly pointing not north, but toward the same specific corner of a room. This strange alignment is the most compelling clue pointing to the existence of a hidden giant, a hypothetical world astronomers call Planet 9. The idea is that a super-Earth, up to 10 times the mass of our own planet, is tracing a vast, elliptical loop far beyond Neptune. Its immense gravitational pull, exerted over millions of years, would act like a shepherd's crook, gradually nudging the orbits of these smaller, icy bodies into the strange clustered pattern we observe today. But for all the elegance of this theory, the planet itself remains a ghost. Extensive searches across the sky have yet to find any direct sign of it, leaving its existence as one of the most tantalizing what-ifs in modern astronomy. In the absence of a single, large perturber, scientists have explored other possibilities. Could the collective gravity of countless small, unseen objects in the Kuiper belt be responsible? Or perhaps the orbits were sculpted this way by instabilities in the primordial disk of gas and dust from which the solar system formed. Yet these alternatives struggle to replicate the precise, sustained alignments we see. The orbits of these distant ice worlds are a fossil record of the solar system's earliest days, and they seem to be telling a story of a dramatic gravitational encounter that our current maps cannot account for. This great unresolved puzzle at the very edge of our planetary system forces a profound question. How well do we truly know our own cosmic neighborhood? And if our census of the outer solar system is so incomplete, what other gravitational surprises might be hiding much closer to the Sun, in the sweltering region where worlds race around our star in a matter of days? Mercury's path around the Sun is not a perfect repeating ellipse. Instead, it slowly rotates like a spirograph drawing that gradually shifts its pattern over time. Astronomers call this the precession of its perihelion, the slow drift of the point where the planet swings closest to the Sun. For centuries, this drift was measured with increasing precision. Newtonian gravity, which so beautifully explains the orbits of the other planets, could account for most of this motion. The gravitational tugs from Venus, Earth, and the other worlds were constantly nudging Mercury's path. But a tiny sliver of the precession remained stubbornly unexplained, a discrepancy of just 43 arcseconds per century. In the grand scheme of the solar system, this is an almost imperceptible amount, a deviation equivalent to the width of a human hair seen from a kilometer away. Yet this minuscule error was a crack in the foundation of classical physics. It was a signal that something was missing from our understanding of gravity itself. The mystery was finally solved by Albert Einstein. His theory of general relativity proposed that gravity is not a force acting across a distance, but the result of mass and energy curving the very fabric of spacetime. The Sun, as the most massive object in our neighborhood, creates a profound dimple in this cosmic fabric. As Mercury, the fastest planet, races through this curved spacetime on its tight orbit, its path is ever so slightly altered. The planet does not simply orbit the Sun, it follows the contours of a warped stage. Einstein's calculations showed that this curvature precisely accounted for the extra 43 arcseconds. The explanation was a monumental triumph, turning a celestial anomaly into a stunning confirmation of a revolutionary theory. But the story does not end there. Mercury's orbit remains one of the most sensitive testing grounds for the laws of physics. Modern laser ranging and spacecraft tracking measure its motion with breathtaking accuracy, scrutinizing Einstein's prediction to see if it holds perfectly. Any tiny deviation from what general relativity demands could be a beacon pointing toward new physics. Perhaps it would hint at a subtle flaw in our understanding of gravity, or suggest the presence of unseen matter, like a swarm of small, dark asteroids lurking even closer to the Sun, their collective gravity adding an unseen tug. This little world, scorched by solar fire, serves as a natural laboratory where the deepest laws of the universe are continually put to the test. Its successfully solved mystery stands as a powerful reminder that the greatest puzzles in our solar system are not dead ends, but invitations to see the cosmos in an entirely new light. We feel the sun's warmth on our skin, a gentle heat radiating from its visible surface, the photosphere, which burns at a relatively cool 6,000 degrees Celsius. Yet high above this familiar layer, in the wispy, ethereal outer atmosphere called the corona, the temperature soars to a blistering 1,000,000 degrees or more. This is the coronal heating problem, a paradox that defies basic intuition. How can the atmosphere be hundreds of times hotter than the surface it surrounds? It is like walking away from a fire and stepping into an inferno. The energy must come from beneath, but the process of transporting it upward remains one of the sun's greatest secrets. Scientists suspect the sun's tangled magnetic field holds the key. One leading idea involves nanoflares, a constant rain of tiny, unseen magnetic explosions that ripple across the corona. Each one is minuscule, but collectively they could provide a steady drizzle of heat. Another process, magnetic reconnection, occurs when opposing magnetic field lines snap and realign, releasing colossal bursts of energy in a celestial short circuit. A third theory points to powerful waves of energy called magnetocaustic waves that travel upward from the churning surface below, crashing into the corona like ocean waves on a shore and dissipating their energy as heat. Yet no single mechanism seems sufficient on its own. The corona is likely heated by a complex chorus of all these processes, their contributions changing from moment to moment across the sun's dynamic face. This is far more than a theoretical puzzle. The corona is the source of space weather. Its intense heat and complex magnetic fields give birth to solar flares and coronal mass ejections, billion-ton clouds of plasma that can race toward Earth. When these eruptions strike our planet's magnetic shield, they can trigger breathtaking auroras, but also cripple power grids, disrupt satellite communications, and endanger astronauts. Understanding how the corona is heated is the first step toward predicting its most violent outbursts. The star that gives us life is also a master of cosmic chaos, and its most fundamental processes are still being decoded. If our own sun, the one star we can study in intimate detail, holds such a profound mystery, what does that say about the trillions of other stars lighting up the cosmos? Even the orderly chaos of the Kuiper belt is confined by a wall. Far beyond Neptune, this vast disk of icy worlds does not simply fade into the emptiness of interstellar space. Instead, it reaches a sharp precipice, an outer edge so abrupt it defies the very idea of a gradual frontier. At about 50 times the Earth-Sun distance, the population of these frozen objects plummets. It is not a gentle thinning, but a dramatic drop-off, as if the solar system were contained within a cosmic bowl with a surprisingly steep rim. This sharp boundary presents a profound problem. The cloud of gas and dust from which our planetary system formed should have extended much farther out, seeding icy planetesimals across a far broader region. We would expect to find a sparse but steady population of objects for hundreds of astronomical units, a fading echo of the primordial disk, yet the observations tell a different story. The Kuiper belt ends, and it ends with a definitive cut. How does a solar system build a fence around itself? One compelling idea looks to the sun's infancy when it was still nestled in its stellar nursery. A passing sibling star moving close to our young solar system, could have gravitationally sheared off the outer reaches of this disk, stripping away the most distant material and leaving behind a sharply truncated belt. Another hypothesis returns to the possibility of an unseen planet, a distant shepherd whose gravitational influence defines this outer edge, clearing a path through the chaos over billions of years. Yet a third force to consider is the gentle but persistent pull of the galaxy itself. As our solar system orbits the Milky Way, galactic tides may have slowly eroded the outermost objects, tugging them away into the darkness. But each of these elegant solutions has its flaws. A stellar flyby is a one-time event that seems almost too fortuitous. An unseen planet remains frustratingly hidden, and galactic tides act far too slowly and weakly to create such a clean, dramatic edge. This boundary is more than just a line on a map. It is a fossilized record of a violent or highly structured youth. Its existence implies that our solar system's formation was not an isolated event, but one likely influenced by external forces from its very beginning. This sharp edge forces us to look past our own cosmic neighborhood and acknowledge that we may have been shaped by stellar visitors long since gone. It challenges us to define where our solar system truly ends, not in a vague cloud of comets, but at a definitive border we are only just beginning to perceive. Our solar system's final frontier is a ghost, a vast and unseen sphere of ice that may not even be there. This is the Oort cloud, a hypothetical shell of frozen worlds beginning roughly 2,000 times farther from the Sun than Neptune and stretching perhaps halfway to the nearest star. We have never seen a single object within it, nor has any spacecraft ventured anywhere close. Its entire existence is a deduction, a necessary conclusion drawn from the paths of long-period comets. These icy visitors arrive from every direction, on orbits lasting millions of years, and the only way to explain their random approach is to propose a vast spherical reservoir surrounding us. Its theoretical structure is a relic of our solar system's most violent era. In the chaotic youth of the planetary system, the newborn giant planets acted like gravitational titans, flinging countless icy planetesimals away from the Sun. Some were ejected into interstellar space forever, but a vast number were thrown just hard enough to reach the very edge of the Sun's gravitational grasp. There, in the profound cold and darkness, they found a precarious balance. They are so distant that the gentle tugs of passing stars and the overarching gravity of the Milky Way galaxy itself are enough to perturb their orbits, occasionally sending one on a fall into the inner solar system as a new comet. This elegant story, however, is built on a foundation of complex models that are nearly impossible to verify. How many objects truly reside in this cloud? Is its distribution smooth, or are there vast, empty voids and dense clusters shaped by galactic forces over billions of years? We simply do not know. The Oort cloud represents the ultimate limit of the Sun's influence, a place where its gravity finally yields to the pull of the galaxy. This blurs the very definition of our home, challenging us to decide where the solar system truly ends and interstellar space begins. Contemplating this distant, invisible shell ties every other anomaly together. The lopsided magnetic field of Jupiter, the sideways roll of Uranus, the captured moon Triton, and the truncated Kuiper belt all point back to that formative age of chaos, the same era that likely filled the Oort cloud with its frozen trillions. It is the ultimate reminder that our solar system is not an isolated island, but a dynamic structure, continuously shaped by its galactic environment and forever holding the secrets of its birth in the frozen dark. These cosmic riddles are far more than isolated curiosities. They form a single, sprawling tapestry of ignorance, revealing the vast frontiers where our current science simply breaks down. Every unexplained tilt, every lopsided magnetic field, and every erupting geyser is a challenge to the neat, orderly models we once believed were complete. They force us to admit that the solar system is not a static museum exhibit, but a dynamic and often violent system whose history is written in codes we are still learning to read. These puzzles are the very engines of discovery, pushing the limits of our technology and imagination. To solve the mystery of a hidden ocean on a distant moon, we must build probes capable of tasting its geysers. To map the contours of a hypothetical ninth planet, we need telescopes that can scan the deepest, darkest voids. Each anomaly is a destination, a scientific question that demands a new mission, a new instrument, a new way of seeing. This relentless pursuit answers a fundamental human need, the deep-seated drive to explore and to comprehend our true place in the cosmos. We are on the cusp of a new golden age of exploration. Powerful new observatories are coming online, and ambitious missions are being planned to touch the clouds of Venus, to sail the methane seas of Titan, and to search for life in the subsurface waters of Europa. The very mysteries that baffle us today are the beacons that will guide these voyages of tomorrow. They are not dead ends, but invitations to a grander, more wondrous understanding of our celestial home. From Saturn's perfect hexagon to the ghostly Oort cloud, these 25 cosmic riddles paint a clear and humbling picture. Our solar system is not a solved puzzle, but a living, breathing laboratory of the bizarre, a treasure trove of mysteries that refuses to be neatly catalogued. Each of these anomalies is a direct challenge to our understanding, forcing astronomers to refine their theories, to build more powerful instruments, and sometimes to tear up the textbooks and start again. The journey through these enigmas reveals a profound truth. Every gap in our knowledge is not an endpoint but an invitation. It is an opportunity for a discovery so fundamental it could reshape science itself. The universe, as one physicist noted, is under no obligation to make sense to us. Yet our relentless human curiosity, that drive to look up and ask why, ensures we will never stop trying to understand it. If these cosmic puzzles have captivated you, consider subscribing for more deep dives into the greatest mysteries of space, and we would love to hear your thoughts. Which of these 25 anomalies do you find the most utterly baffling? Let us know in the comments below.